Good day to each and everyone. So for this video, we are going to talk about another type of force that we can actually utilize in our analysis using Newton's laws of motion, and that is your frictional force. If you notice, up until now, we have been neglecting the effects of friction on the motion of the object, as can be seen in our previous examples from the videos that I presented to you. In fact, in most of those examples, I always state there that the surface is frictionless such that we can ignore the effects of friction in our analysis. But in reality, we cannot really avoid friction because no matter how smooth the surface is, there will always be a certain part of that object that tends to be rough at the microscopic level. So that is why in real life we cannot really avoid including friction as one of the factors that affects the motion of our object. So how do we technically define friction? So as what I have researched, friction is actually a force that resists the motion of two surfaces, either sliding, rolling, or moving past each other. Okay? So since friction is a force that resists the motion, then that means it always acts on the opposite direction of the force applied on the object. So if you're applying a force to the right, your frictional force will tend to resist this force, so your frictional force will point to the left, and so on and so forth. If your force is applied on the left, then the frictional force is opposing this applied force, so your frictional force points to the right, so on. Now, there are different types of friction as I have researched on the internet, and these are as follows. Number one is a static friction. Now, when you say static friction, this is a type of friction that governs objects that are at rest or not moving. And in order for you to start a motion, you must overcome this static friction that is occurring on the object. Moving on, when you say kinetic friction or sliding friction, these are friction that acts on the object that are sliding past each other. So whenever you push an object and it starts to moving, it is actually the kinetic friction that opposes this force that you are applying. Next is the rolling friction, in which this is a frictional force that acts when the objects roll over a surface, like for example, a rolling ball or even a wheel. And then, last but not the least, we have the fluid friction, in which it acts when objects move through a fluid, for example, air friction. So these are the types of frictional forces that can resist the motion of two surfaces. But in this discussion, I would only focus on the two types of frictional forces in our analysis, in which we will focus on the static friction and the kinetic or sliding friction. And we shall analyze how the static friction and kinetic friction somewhat affects the motion of the object as we apply force onto them. Now, it is noteworthy that your frictional force, whether a static or kinetic one, is always acting parallel to the surfaces where the objects are moving. So, in fact, there is an experimental establishment of the relationship between the frictional force and the normal force acting on the object, and we can actually write this relationship. I would like to denote a certain symbol here that we'll use throughout our equations, in which F sub Fr is what we will refer to as our frictional force. Okay? And of course, F sub n would be our normal force. Okay? And of course, our coefficient of friction, which we will call as a Greek letter mu, that is the Greek letter mu, in which this will denote as our coefficient of friction. In fact, an experimental relationship between these three quantities have been established in such a way that in order for you to get frictional force F sub Fr, that is actually equal to the constant of proportionality, which is our mu times your normal force. Okay, this is now the equation to get our frictional force. Okay, and depending on the type of friction that is involved, we can always denote mu as either a static friction or a kinetic friction. So to distinguish between the two, I'm going to use the mu s for static friction. Okay, this is for static friction, and I'm going to denote mu with a K symbol as your kinetic friction, just to denote between the two. Okay, so therefore, if I'm going to rewrite the equations for this, for the frictional force involving static friction, that would be mu sub s multiplied by your normal force, and this is for static friction. Okay, and of course for the kinetic friction, our frictional force is given as mu sub k times your normal force, which is for kinetic friction. Okay, there's a big difference between static friction and kinetic friction, as what I discussed a while ago, because objects that are not moving are governed by your static friction, and in order for you to make this object move, you have to overcome the frictional force due to the static friction. And when the object is moving already, then it is not the static friction anymore that works there, but instead it is the kinetic friction. And in fact, we have here some coefficients of frictions from different surfaces that are known to us. As you can see here, these are the coefficient of static frictions and coefficients of kinetic friction. Notice that since this is a constant of proportionality, there is no unit for this. Okay, and there are well-known coefficients of static friction and kinetic friction from different known materials here, so you can just check it out. And what we can also somewhat derive from the coefficient of static friction is that the higher the value of your static friction, the rougher the surface gets. So for example, our coefficient of static friction here for wood is around 0.4. That means that of all these listed materials here that you can see, wood is the roughest surface. But of course, we know that wood is not the roughest surface, but it's just that on this table itself, wood is the roughest surface. Okay, so for the coefficient of kinetic friction, as you can see, the coefficient of kinetic friction is somewhat lesser in value than the coefficient of static friction. It's because the object is already moving there, so therefore there is somewhat a lesser tendency for this object to resist the motion of the objects being applied with a force. Okay, so that's how we are going to understand these values here. So let's just say, for example, so that we can further understand the effects of this friction here, let's consider this system here. Again, allow me to use a box for simplicity. Okay, for instance, I have a box here that is static, meaning to say this is at rest. We have here, let's just assign a mass here, which I always use here for 10 kilograms. And this object is completely lying on a flat surface. Okay, let's just imagine that this is a flat surface, but this surface has a coefficient of static friction. Sorry, allow me to change the symbol. Has a coefficient of static friction which is around 0.4, and we know that 0.4 is wood, right? So let's just say that I have placed this box in a wooden surface with a static coefficient of static friction which is around 0.4. Okay, now let's calculate the static friction on this box here. But before that, let's first identify what are the forces that are acting on this box that is at rest. First is, of course, you have your downward force due to the mass of the object, in which we will denote this as your Fg, or your gravitational force, or technically the weight of your object, which is, of course, we know that that is mg. And if we further calculate that, we have here our 10 kilograms multiplied by your constant of gravitational acceleration, which is equal to 9.8 meters per second squared. That is equal to 98 newtons going down. Okay? And of course, you have also the upward force, the perpendicular force, which is your normal force, which in this case is equal to Fg, which is also 98 newtons. But of course, the direction of your 98 newtons for your normal force is going upward. So therefore, it's a positive value, while your gravitational force here is going downward, so it's somewhat in a negative value. Now, in order for us to calculate the frictional force of this frictional force experienced by this box, all we need to do is, again, just write the equation for the frictional force using our static friction coefficient, which is mu sub s multiplied by your normal force. Okay? So therefore, we can substitute this value right now. R is equal to, our mu sub s there is around 0.4. Okay? That is 0.4 multiplied by 98 newtons. Therefore, our frictional force due to the static friction of the floor is equivalent to, if we are going to calculate that one, that is 98 times 0.4. How much is that? Let me use my calculator first. 98 times 0.4, that is 39.2 newtons. This is the amount of frictional force that is present on the box due to the rough surface of your wood. Now, what does this imply? Now, this is how you're going to understand this. In order for you to move this box, you must overcome a frictional force of 39.2 newtons. Meaning to say, unless the force that you apply is bigger than the frictional force, this box will not move. So the condition is for the box to move is that your force applied, which I will denote as F sub P, should be greater than the frictional force due to your static friction. Let me just denote that one. This is due to the static friction. It must be greater than the static friction. And object will move. Let me just denote it here. Object will move. Okay? But if the force applied, or your F sub P, is less than the frictional force due to the static friction, then object will not move. Okay? So, for instance, if I'm just going to push this object with only 20 newtons, then that object will not move. But if I apply a force of, let's say, 100 newtons, that object will start to move. And when that object will start to move, it is not the static friction that works anymore, but instead, it will be the kinetic friction in this case. Okay? So, that's how you're going to understand this particular example. Okay? So, let's proceed to the next. Now, let's consider this very simple example so that you will understand further the concept of static and kinetic friction. Let's say, for instance, that again, let's have our box again here, which we will put on a surface. Let's just imagine that this surface is rough. Then, let's just say that the surface has a static friction of around 0.4, just the same as a while ago, and a kinetic coefficient of friction of 0.3. And let's say that the mass of the object is around 10 kilograms still, so that it will make our calculations easier later. Now, let's just say that this box rests on this floor. And what we are going to do right now is to determine, first, let's write here for letter A, determine the frictional force, or F sub Fr. Okay, the frictional force acting on the box if a horizontal force, which I will call as, let me just write the complete words here. So what we are going to do now is calculate the frictional force on the box if a on the box. Okay, let's just write it here. On the box, if an applied force, which we will call as F sub P, okay, is exerted on it with the following magnitudes. Let's say here, letter A, 0 newtons, and letter B, let's have 10 newtons, and letter C, let's have 40 newtons, and then letter D, let's have 38 newtons. Okay, so basically what this question would like to tell us is that if a force, which we refer to as F sub P, is exerted on this object, and we can assume that maybe the force was exerted on this direction, F sub P there, we want to calculate the frictional force on the box if an applied force F is exerted in it with the following magnitudes. A, if we exert the box with 0 newton. Letter B, if we exert the box with 10 newtons of force. C, if we exert the box with 40 newtons of force. And letter D, if we exert the box with a force equivalent to around 38 newtons. So how are we going to approach this problem? Well, technically, this is somewhat a very easy approach to somewhat deal with, because what you're going to do is that simply first get and calculate the frictional force due to the static friction of the box, because the box is completely at rest at this initial condition. So our first step here is to calculate the frictional force due to the static friction. Okay, so that is unknown yet. So that means Fr is equal to the mu of our static friction times the normal force. And we know for the fact that our normal force is equivalent to our force of gravity here. Okay? Because our force of gravity, as what I've mentioned a while ago, our force of gravity is just equal to the weight of the object, which is m times g, and we calculated this a while ago. So therefore, this will become 0.4 multiplied by the mass of the object, which is 10 kilograms, multiplied by 9.8 meters per second squared. So our answer here would be equivalent to what we calculated a while ago, which is 39.2 newtons. So this would be 39.2 newtons. So this would be our frictional force due to the static friction of our surface. So this is our preliminary step towards our answer in letter A to letter D. Now, let's try to identify right now whether these forces have an effect on the how do you call this? These forces have an effect on your object. Okay? So therefore, for letter A, if the force applied, or Fp, is equal to 0 Newton, then we know that this object will not be able to cause this object to move because it has to overcome 39.2 newtons of force. So therefore, it has no effect. Meaning to say, object will not move. Object will not move. And if the object will not move, the value of its it's not letter B. If the object will not move, the value of its frictional force is the same as the frictional force due to the static friction, which is 39.2 newtons. So our answer here would still be the same. Okay, still 39.2 newtons. Clear? Okay, so I hope that we are making ourselves clear here. Okay, so sorry, it's not, sorry, this is a misconception. So if you apply the force of 0 newton, then technically your frictional force there should also be 0 newtons, because according to the Newton's second law, the sum of all the forces of the object that is at rest should also be should equal to 0. So therefore, since 0 newton is applied, so our frictional force should also be 0 newton. Sorry for that. Okay, so let's now have letter B. Okay, for letter B, what if the force applied is 10 newtons? Still the same, because again, this 10 newton force applied cannot overcome the frictional force due to the static friction, which is 39.2 newtons. So therefore, the box will still not move. So therefore, our frictional force here should also be 10 newtons, but on the opposite direction. So it is a negative sign. Okay, I did not put negative on the 0 because there is no such thing as negative 0. So this is negative 10 newtons. So that is our value for our frictional force for this case. Again, you might ask, why, sir, this is negative 10 newtons? Because again, your 10 newton force cannot overcome the 39.2 frictional force due to the static friction. So therefore, the sum of all the forces here is equal to 0. So if you apply a 10 newton force, then an equal 10 newton force is applied, making the net force 0. So the object will not move. How about for letter C? For letter C, that is of course 40 newtons. Now, 40 newtons, as you can see here, is bigger than your FFR, which is equal to 39.2 newtons. So therefore, if you apply with this force, the box will move. Okay? So now that the box will move, I told you a while ago that if the box will move, or an object will move, it is not the static friction that governs this object anymore, but the kinetic friction. So in order for you to calculate the kinetic friction for this case, because the box is now moving, we need to apply the equation for the coefficient of kinetic friction, in which FFR right now is equal to the mu of your K, or kinetic friction, times your normal force. Okay, so to calculate this, all we need to do is just recall that our mu of our kinetic friction is 0.3 newtons multiplied by what is now our normal force, that is 10 kilograms multiplied by 9.8 meter per second squared. So therefore, our F sub FR here, sorry, allow me to erase this first. Okay, our F sub FR here should be equal to 0.3. Let's multiply that. 0.3 times 9.8 times 10. So this is around 29.4 newtons. So therefore, our coefficient of kinetic friction here would be 29.4 newtons. Okay, so this is now 29.4 newtons. Let's box that one. That is now the value of our kinetic friction for this case. Okay, so that's the answer for letter C. And of course, for letter D, since letter D is 38 newtons, F sub P is of course 38 newtons. That is still less than 39.2 newtons. So therefore, our frictional force there is still negative 38 newtons. Okay, let's box this answer. And that completes our analysis here of the effects of frictional force on the motion of the object as described by the coefficients of static and kinetic friction. And there are still more examples that we can actually utilize for this one, so I will just leave it on our next video. So I will stop from here right now so that you can rest. Okay, so thank you so much for listening to our discussion for today, and I hope to see you for our next video presentation. Bye!